Please join me in welcoming Gillian Russell. She's a professor of philosophy at Dionia Research Institute at ACU, and she has very kindly agreed to come here and talk to us about her work. So I'll leave it over to Gillian here.
Thanks very much, Sebastian. Thank you to all of you for showing up to listen and talk about this stuff. So the paper is called How the Laws of Logic Lie. There is a handout, which I think Sebastian has emailed to people, but I'm also going to share the screen so that we have something to look at apart from me. So let me just find that. Okay, so I hope that people can see the handout now. Okay, one of the things I wanted to apologize for is that the handout is so out of control. So I think there are like 12 pages for it. My only defense is that it was much worse yesterday. And so it's at least improved. It's very new material, and I hope that as I get more in control of it, the handout's going to get more succinct. But I would really appreciate your help in kind of refining it. Okay, so I hope that the title is legible, at least to some people, as an homage to Nancy Cartwright's 1983 book, How the Laws of Physics Lie. And in that book, Cartwright argues that theories in physics make frequent use of idealization. For example, they talk about point particles, which are kind of idealized particles. They don't exist in the real world. And because of this use of idealization, the theories end up being, she always says not true, but I think we can safely say false in this talk. I'm not going to lay a lot on the distinction there. Okay, so what I am going to do in this talk is talk about the ways in which we can think of logic, and especially model theory, as idealizing and basically modeling the relation of logical consequence on natural language, idealizing natural language and the meanings of natural language expressions in various ways, and then seeing if, as a result, some of the laws of logic end up lying, end up not being true. So that's the overall project. Although the handout is really, really long, there are just 3 sections to it. So the first section is sort of preliminaries. I'm going to talk about modeling in science and then how we do something similar in logic. And the second section, I'm going to look at Cartwright's arguments that when we do theorizing with idealizations in physics, we end up with laws that are false. And then the last section is going to be about laws of logic and how idealization in logic gives us laws that are false. So that is where we're going. So first section, it's really common when scientists are studying complex phenomena for them to build models of the phenomena that they're interested in. So for example, if you're a meteorologist, you might build a model of a hurricane. Usually that would be a computer simulation, and there will be parts of the simulation that corresponds to things in a real hurricane, like the wind speed, or like the ocean temperature, or the air pressure. Similarly, if we're modeling a pandemic, then we might have various things in the model that correspond to things in the real world, such as the R value for the disease, like how many people get infected by every person who gets infected. Yeah, okay. So these days, they're often computer simulations, but they don't have to be. So we still have some like physical models that we can use in science. So an orrery is one of those models of the solar system that has like the physical spheres on wires that rotate around the center of the system, and you can use them to predict things like when there's going to be an eclipse or when two planets are going to be close to each other. Or a river flow simulator. That's a kind of sandbox on an angle with a water inlet at one end, and you can use it to build a model of a river and then investigate various things like erosion patterns and things like that. And of course, animal models of disease, they're physical models in which things really happen, not just computer simulations. So the computer simulations can be very complex, but they're usually not as complex as the target phenomena. So if you think about air temperature in a hurricane, that's a ferociously complex thing. So the temperature is not going to be constant throughout the hurricane. And even in small parcels of air, there's going to be variation in temperature over distance. And when it comes down to it, the temperature is a matter of the velocities of these tiny molecules inside the air, or that make up the air. And there's nothing that corresponds to all that in the computer simulation. Normally we'll have something simpler, like average air temperature in a certain parcel of air. And that's what will go into the model to represent air temperature. Physical simulations, they can be extremely complex themselves. So if you have one of these river flow sandboxes, like the temperature in, say, a cubic foot of sand is going to be extremely complex. But it's only some parts of the simulation that are supposed to represent some parts of the target phenomena. So we're not trying to represent exactly the temperature of some section of the riverbank. We'll probably have certain features that we're aiming for, like, say, the flow speed of the water, maybe the actual shape of the river and the depth of the water, and the angle at which the sandbox is limited might be the steepness of the hill down which the river flows. So the actual parts of the physical simulation that are doing the representing are not as complicated as the phenomenon that they're simulating. This is intentional, right? So the simulations of hurricanes and rivers, we don't want them to be as complex as the things that we're simulating. If we modeled hurricanes by trying to get an exact representation of the temperature throughout the hurricane, well, first of all, there's more data there than we can possibly collect. It would take way too much time. And then we'd have so much data that just inputting it into the simulator would take forever. And there'd be a question about whether the computer was actually going to be able to give us predictions about, say, where the hurricane is going to be tomorrow in time. So it's much more useful to have a simple simulation that is easy to use than it is to have one that's perfectly accurate. And some of these literary quotes down the side of the handout, I wonder if I can move that over a little bit, are hinting at that fact. So there's this quote from Lewis Carroll from this novel from 1893, and it's a conversation. So one of the people is saying, we very soon got to 6 yards to the mile. Then we tried 100 yards to the mile, and then came the grandest idea of all. We actually made a map of the country on the scale of a mile to the mile. Have you used it much? I inquired. It has never been spread out yet, said Meinherr. The farmers objected. They said it would cover the whole country and shut out the sunlight. So now we use the country itself as its own map. And I assure you, it does nearly as well. Similarly, there's a Borges story about a map that's made that's the size of the country, and how later cartographers don't think this is as useful as you might have hoped, even though it's very, very accurate. And then, putting it straight, Nancy Cartwright in How the Laws of Physics Lie, she says, we should not be misled into thinking that the most realistic model will serve all purposes best. Okay, so the simulations are not necessarily perfect simulations of what they're simulating, but that's the point, right? That's not a problem. That's intentional. Okay, so what about logic? So historically, philosophers have thought of logic in different and incompatible ways. I guess some of that was coming up at the beginning when I was talking to Professor Kraut. Some people think that logic is like the study of the normative laws of thought. Some people think it's like the conditions on thinking as such. Various different things. What I'm going to do here is pick one particular strand in thinking about logic that is unashamedly like conducive to my project, and run with that. So the most famous representative of this way of thinking about logic, I think, is Frege. And here he is in The Thought, expressing the idea that logic is the science of truth. So logic has much the same relation to truth as physics has to weight or heat. To discover truths is the task of all sciences. It falls to logic to discern the laws of truth. The word law is used in two senses. When we speak of laws of morals or the state, we mean regulations which ought to be obeyed, but with which actual happenings are not always in conformity. Laws of nature are the generalization of natural occurrences, with which the occurrences are always in accordance. It is rather in this sense that I speak of the laws of truth. So the idea is physics describes, say, preservation of heat over various physical changes, and logic describes the preservation of truth over sentences, say, in arguments, that is the relation of validity, logical consequence. It's not the only thing logic does, right? So this is just like one part of logic, but I think it's one important part of logic, trying to capture the consequence relation. So we can think of the model theory for a logic as simulating the relation of logical consequence on a natural language. So natural languages are very complicated. They involve, say, vagueness or reference failure, the self-reference, tense and aspect, lexical and scope ambiguity. Some people think they even contain contradictions, if they're like semantically closed. But the presence of validity can depend on such things, that it depends on what the expressions mean. And so if the expression is vague or the expression lacks a reference, that can be relevant to whether or not the argument is valid. So in order to study consequence, we construct simpler languages with stipulated syntax and meanings, simulations. In the interest of concreteness, I'll introduce a specific example here. It's an ordinary model theory for first-order logic. There shouldn't be anything special or surprising here, but specifying the details will give me something to refer back to for clear examples later in the paper. Okay, so there is a model theory for first-order logic here. It is just for concreteness. So I'm not going to talk through every single clause in these definitions, but you'll see that we've got a list of primitive expressions in the language. So there's like some individual constants, some variables, we've got predicates, we've got truth functional connectives, we've got the quantifiers, and punctuation. We'll need that as well. And then the next thing is definitions of the complex expressions in the language. So we have well-formed formulas or WOFs. That's a recursive definition. So this base clause tells us if you get a predicate and you feed it enough terms to fill up all its arguments, then you get a WOF. But you can also get WOFs by negating WOFs you have already, or conjoining them, making them into conditionals. You can quantify into them. Okay, so probably in the full version here, we talk a bit about the scope of quantifiers and closed and open WOFs. But I'm just going to jump straight to saying a sentence is a WOF with no free variables. And then we've basically got our syntax, right? We've got the simple expressions, we've got the complex expressions, and we know what a sentence is. And the next step is to think about meanings. Like, how do we simulate some of the meanings that these expressions have? Well, it's done in various different ways. So there's at least 3 different ways in first-order logic in which expressions are given meaning. One of these ways is you can have an interpretation assigned by one of the first-order models. So our models are going to be these pairs of a domain, it's like some non-empty set, and an interpretation function. And the interpretation function assigns like reference to the individual constants and suitable extensions to the predicates. So you can think of that being like one sort of idealized representation of the meanings of names or the meanings of predicates. But not every expression gets a meaning from the interpretation function. Variables get their extensions from a variable assignment, so just a function that assigns them some denotation in the domain. And then the logical expressions get their meanings in different ways via the recursive clauses in the definition of truth in a model on an assignment. So I've like just put in some representative clauses there. So the have the truth conditions for atomic sentences, but then the negation of some sentence is going to get the value 1, just in case. Sorry, there's an extra negation in there that I should have deleted, just in case that should be phi, gets the value 0. Okay, or maybe to find an example that's actually not got a typo in it, the conjunction phi and psi is going to get the value 1, just in case both conjuncts get the value 1. Okay. So we've got some like different ways in which the expressions get assigned sort of idealized meanings, but the whole point of the model and the model theory was to simulate this relation of logical consequence or validity on the language. So we're going to need to like define up logical consequence, and since we do that in terms of truth in a model, we need more than just truth in a model on an assignment. So we need this definition here, phi is true in a model, that's just truth on every assignment. And then we can define what it is for something to be a logical truth in the language, is to be true in all models, and what it is for a conclusion phi to be a logical consequence of a set of premises gamma. It's that every model of gamma is a model of phi. Okay, so hopefully no big surprises there. I'm going to talk more about particular examples of idealization and logic later, but I think there's already some sort of suggestive, promising candidates that I can gesture towards. So here are some. The assumption that all names have exactly one reference. So that's built into the definition of the I function. In a model, you assign like one reference to every individual constant. There are no ambiguous names or names that fail to have a referent, as you might think there are in English, like say Pegasus or Vulcan. And so you might think this is kind of an idealization of the way names get meanings in English. There are no context-sensitive expressions in this language, so the quantifiers, they just always quantify over the entire domain. There are no like separate subsets assigned given different contexts. There are no indexical terms or operators, and sometimes that can affect the validity relation. We've got the assumption that each predicate has a determinate extension, and in particular that the extension is complete, whereby I mean that you have some predicate P and its extension is some subset of the domain, and then there's a set of things that satisfy not P. And in classical logic, the way we've just set things up, the union of those two sets is the entire domain, right? But you might think that, and there are various philosophical motivations for thinking that you could have a predicate where there's a set of things which are P and a set of things which are not P and some other stuff, right? So that there are things that are neither in the extension nor in the anti-extension of P. And if there are predicates like that in English, then this assumption that every predicate just gets assigned an extension is going to be an idealization. One question we can ask is whether the model as a whole is an idealization of something. So if you take that pair, the domain and the interpretation function, is that supposed to represent something? Does it do so in an idealized way? And if you're a fan of Etchemendy's concept of logical consequence, and I'm a fan of Etchemendy's concept of logical consequence, then you're probably aware that there are at least two different standard ways of thinking about what models represent. So one way that is pretty common in philosophy is that people think of that as representing different ways the world could be. So if you have a model in which, say, FA is true, and a model in which FA is not true, then you're basically representing two different ways the world could be. One in which A is F, and one in which A is not F, right? And then the logical notions are sort of modal notions. There's a different way of thinking about what models represent that has more in common with Tarski's original view, and you find it a lot in Quine when he's doing philosophy of logic, that what a model represents is an interpretation of the non-logical expressions in the language. Different models represent different interpretations of the non-logical expressions, and so sort of different possible languages. I'm actually more attracted to the view in which models represent both. So a possible world combined with an interpretation of the non-logical expressions on the language. Call that the combination view. It's a view that you find in Guy Lachère and Stuart Shapiro. And also, I have a new paper endorsing this kind of view. I don't want to get into the argument between those different possible views in the present paper, except to observe that if models represent any of these things, they do so in a highly idealized way. So if you want to represent a possible world and you do it with a non-empty domain and an I function, that's a highly idealized representation of a possible world. Okay, last thing for this section. What is a law of logic exactly, right? So the paper is called How the Laws of Logic Lie. We're going to be comparing physics with logic. We've got these laws of physics that Cartwright says are false, but what counts as a law of logic? So the definition of validity quantifies over models. It's not just one model that it looks at. You need to make the conclusion true in every model that makes the premises true. That means that the truth of something like, and this is modus ponens, phi, if phi then psi, therefore psi, depends on what happens in more than one model, certainly on more than just the most realistic model. But something analogous holds with scientific simulations and laws too. When it comes to establishing laws, such as the ideal gas law, the equation is meant to hold in all the simulations, not just the one that corresponds to the actual world. And more generally, the logical properties are the ones that we can represent with claims in which the double turnstile is the main predicate. So here we've just got logical truth and logical consequence. So we're attributing logical truth to the law of excluded middle, phi or not phi, and logical consequence to modus ponens. And I'm going to suggest that if things with that kind of form are true, then they're laws of logic, right? So I guess I put that in somewhat badly, but this is the things that have the right form to be laws of logic. And let's say if they hold in all the models, then they're laws on that theory. Okay. So I say there isn't much regimentation here, that is, on how to use the word law in logic. But principles such as this are quite naturally referred to as laws of logic, e.g. the law of excluded middle. And true principles like this, including where there is something to the left of the turnstile, are what I will mean by that phrase in this paper. I need to refine that paragraph because I'm doing it. I'm clearly reading it now. I'm expressing it in such a way that makes my thesis false. So what I need to say is that the principles that come out correct in every model, they're the ones that are going to be laws of the relevant theory, according to the relevant theory. Okay, so we're about half an hour in, we're on to section 2. So section 2 is about Cartwright's view. Why does she think that the laws of physics lie? What does it have to do with idealization? Okay, so here's some stuff about Cartwright's view. She thinks that some laws of physics lie, but not all of them. She distinguishes two different kinds of law. So this isn't something that I was familiar with before reading her work, but I take it it's common in philosophy of science. Phenomenological laws from theoretical laws. The former, the phenomenological laws, describe what happens in a fairly specific physical situation. So they say things like what happens in superfluids or meson nucleon scattering. And then if what they say actually happens, then they're true. So that's not what she's really interested in. She's going to put those aside. The laws that she thinks lie are the theoretical laws. So theoretical laws are abstract equations of fundamental theories, and they seek to explain what happens, not just describe it. Examples include the equation of continuity and Boltzmann's equation, which are thoroughly abstract formulae which describe no particular circumstances. I'm going to go through an example, I think, on the next page. I'm going to use the ideal gas law, which is also an abstract formula that describes no particular circumstances. She argues that these laws are not true since they're supposed to explain, and paradoxically enough, the cost of explanatory power is descriptive adequacy. Really powerful explanatory laws of the sort found in theoretical physics do not state the truth. Okay, that's the view. What's the argument for it? The book actually contains several interrelated arguments for the view. And just so that I don't misrepresent Cartwright, I want to point out that probably the central argument is not one involving idealization. So the most central argument concerns difficulties directly testing the theoretical laws. These laws have no direct consequences for experiment on their own, so you have to supplement them with bridge principles, which tell us what results we would expect to get experimentally if the laws were true. And then these bridge principles are sort of complicated. You have to use your judgment to apply them appropriately. They're not given by the fundamental theory. And so that means the theory on its own doesn't tell us what the results of experiments are going to be. And that means it doesn't describe the world in Cartwright's terms, and so it isn't true. Okay, but I'm just mentioning that to put it aside because the argument that I want to focus on here concerns idealization. As Cartwright puts it, the phenomenological laws are indeed true of the objects in reality, or they might be, but the fundamental laws are true only of objects in the model. This is like highly suggestive, but it's not trivial to spell it out in detail. Like, how do you get from this idea that they're only true of objects in the model to the claim that they're false? So here's a problem for what Cartwright seems to be saying here that I want to spell out and then try to get around. So in one standard way of thinking about it, geometry deals with idealizations. So for example, we get straight lines and triangles, and you might think that they are never found in the physical world. And the kind of things that people say when they're suggesting this kind of thing is, look closely at any physical edge, and you find that it's at least a little bit curved or a little bit bumpy. And in fact, if you look at any physical edge under a microscope, presumably it's going to look bumpy. And so you say, okay, there are no perfectly straight edges in the real world. And if a real world edge is part of a closed three-sided figure, that figure can only approximate a triangle because it doesn't have perfectly straight edges. Okay, so if you think there are no triangles in the real world, you might be tempted to say that a law of geometry, so some abstract equation describing like geometrical forms, like say the Pythagorean theorem. I went to school at a time where we learned this theorem as a squared plus b squared equals c squared. But older people in the UK learned to say it more explicitly. The square of a triangle's hypotenuse is equal to the sum of the squares of the other two sides. So we might say that that is only true of objects in the model. That is kind of the abstract forms, the third realm, not true of any objects in the real world. But the equation is a maybe somewhat disguised universal generalization. If we make it explicit, it begins, for all triangles, the square of the hypotenuse is equal to the sum of the squares of the other two sides. And if triangles are idealizations and there are no triangles in the physical world, then this universal is true of the physical world, just vacuously so. So wouldn't the use of idealization make the laws vacuously true rather than false? We can run this same story in physics as well as in geometry. So the ideal gas law relates temperature, pressure, and volume in an ideal gas. So it says P multiplied by V is equal to nRT, where P is the pressure, V is the volume, T is the temperature, N is the amount of substance, which we measure in moles, and R the ideal gas constant. So what's an ideal gas? An ideal gas is a bunch of point particles moving around, never interacting with each other in a closed system. So the idea is the system is not influenced by anything that's going on outside of it. This incorporates at least 3 different idealizations. We've got the point particles themselves, which don't have any extension, so we don't find them in the real world. The assumption that they never interact, and the assumption that the system is closed, whereas in fact, no real container of gas could be completely isolated from outside forces. So a pretty plausible view is that there are no ideal gases in the real world, just like there are no triangles in the real world. The ideal gas law is, like the Pythagorean theorem, an implicit universal claim. It says that all ideal gases are such that PV equals nRT. So if there are no ideal gases, it's vacuously true of the real world. But if a law is vacuously true, it might be problematic in various ways, but it doesn't lie. So what we have right now, so far, is an argument that laws that characterize idealizations are only vacuously true of the real world. But that doesn't seem like a way of lying. So can we do better, right? Can we get an argument to the view that the laws of physics are false? Okay, let's try this. Since the laws are universal generalizations, they're of the form all f's are G, they would be false if there were f's which were not G. It often feels as if it's being suggested that it's something to do with the fact that real gases don't obey the ideal gas law that makes the ideal gas law false. I mean, as I've construed it so far, the quantification in the law is restricted to ideal gases. And understood that way, the deviant behavior of non-ideal gases is no counterexample. But what if we don't understand it that way? After all, it's already coming out vacuously true, which is hardly an unproblematic status on this understanding. And it seems odd for physics, which aims to tell us how the physical world behaves, to deny making claims about the physical world. So suppose the ideal gas law were instead construed to say, for any gas, not just the ideal gas, is any gas, PV equals nRT. Well, that's false. Right? There are lots of gases that don't obey the ideal gas laws. So I think we can set the problem up for the physicist as a dilemma. Either the law quantifies over ideal gases alone. In that case, it doesn't talk about physical reality and doesn't count as a law of physics. Or it quantifies over real gases as well. And then it's a law of physics, but it's false. So the laws of physics lie, okay? As soon as you construe these equations as laws of physics as telling you about the real world, then they're false. All right. I need to make one last point about idealizations before moving on to logic in section 3. This, I think, is one place where I should actually compress the handout. I should be able to make this in like 2 or 3 bullet points. But here's the idea. I've been talking about idealizations so far as if they're a special kind of object or property. So we've got like point particles, triangles, ideal gases, perfectly straight lines, uniform R values. But there's a different approach in the literature. So sometimes people talk about idealizations as point particles and ideal gases, and sometimes they talk about them as false or unjustified assumptions in a theory. So here's Angela Pochnik in a more recent book. Idealizations are assumptions made without regard for whether they are true, and often with full knowledge that they are false. Here's a couple of examples of this kind of idealization. The conventional assumption in the special theory of relativity that the speed of light is the same traveling away from observers as it is returning to them. We can't establish that. There's no like experimental way to do it. So we just assume it and like do our theory based on that assumption. Or the assumption that a local physical system is closed. So it seems like this is never the case. Outside forces are always going to make a difference to the system, and yet we often make that assumption in theories. The boundary between like idealizations that are special kinds of objects and properties and idealizations that are assumptions, I don't think it's very robust. So that the point particles in a gas don't interact, I think you can either think of that as like a special kind of like object or property of the objects that they don't interact, or you can instead think of it as an assumption that we make in full knowledge that it's false. I think there's a chance that every idealization could be described either way, either as a false assumption or as like a special kind of object. But thinking of idealizations as false assumptions, so in the alternative way to what I've been doing so far, might make it easier to see how they can result in a false theory. So, I mean, if you just think of a theory of a set of sentences and then you add this false sentence to it, then of course that's going to make the theory false. We don't always think of theories that way, especially in science. So you might think of a theory as a set of models representing the set of all like possible evolutions of the physical system, and a law is an equation that holds in all of the models. Making an assumption is equivalent to reducing the set of models. So assume that particles don't interact, you remove all models in which they do. Roughly, the more assumptions we make, the fewer models we have, and the larger the set of equations which come out true in all models, and hence as laws, will be. So if the assumptions are false, one might think that we exclude models that we shouldn't, and hence have more laws than we should. Some of those laws will lie. They are false in situations that we are ignoring for convenience or in the full knowledge that they are possibilities. Okay, that will make some of what I have to say about idealization and logic clearer as well, I think. Okay, so we're on to the last section. So what I'm going to do in this section is look at 4 different examples of idealization and first-order model theory. It's worth saying, I think, that whether or not you think something counts as an idealization will depend on your view of how it behaves in the target phenomenon. So if you happen to think that the air temperature was completely even through all hurricanes, then you wouldn't think it was an idealization in your model of hurricanes that the air temperature is completely even through all hurricanes, right? And similarly, if you think that every name in English has exactly one referent, then you won't think it's an idealization in the model theory to assign every name exactly one referent. Okay. But so, some of this is going to be dependent on people's views, but I'm at least going to suggest that these things could be idealizations, that's one natural view. Okay, so here's the first one. Non-empty domains in first-order logic. So in the model theory in section 1, a model was a pair, a domain, and interpretation function in which the first element is the non-empty set of elements, the model's domain. That requirement of non-emptiness is an idealization. It excludes from consideration models which represent possibilities where nothing exists. And this makes the theory simpler. But here are some of the laws that result. So for example, one, for all x, f of x entails there is something which is f. So everything is f entails there is something which is f. Or 2, you can go from for all x, f of x to f of a, because a has to have a referent and there's got to be something in the domain. There's this formula, there is something such that if it is f, then everything is f, which is a favorite trick formula of logic professors where you have to prove that it's a logical truth. Or the nastier question is it a logical truth? And then you have to either give a counterexample or prove it. And then exists x f of x or exists x not f of x, that comes out as a logical truth, right? I want to suggest that these are actually false. But they come out as laws because we are allowing ourselves to ignore the possibility that nothing exists. So a defender of these laws might be tempted by a response here, But there are no models with empty domains. We defined our models so as to exclude them. I think this is the counterpart in logic of Cartwright's observation that the theoretical equations are true in the idealized models. We retreat to saying that the laws only ever make claims about the models and so aren't challenged by such examples. But in physics, this retreat made the laws no longer qualify as laws of physics. Laws which don't attempt to describe the physical world don't qualify. What I think happens in logic is similar. We back off the challenge of theorizing the target phenomenon, validity, in favor of a relative notion, valid in FOL, or if we're using different models, valid in LP or valid in intuitionistic logic. These relative properties are of interest, but they're not the target phenomenon. They're each attempts to theorize the same target, validity. Anyway, if an argument doesn't preserve truth in some circumstances, for example, in circumstances where nothing exists, then it isn't really valid. So the no empty domains assumption is an idealization, and it's one that leads to laws of logic that lie, namely 1, 2, 3, and 4 above. Okay, that's example 1. Here's example 2. I guess I've mentioned this one a few times, so you won't be surprised by it. All terms have a denotation. So in FOL, each name is assumed to have a denotation, but this is presumably an idealization of natural language names, which can fail to denote, i.e. Vulcan or Homer. The idealization is useful. It saves the need to consider what truth value a sentence ought to receive if a term it contains fails to denote. But a consequence of that is that certain arguments are counted as valid that might not otherwise have been. For example, from everything is F, we can get A is F, because we're not going to worry about the possibility that A doesn't exist, or that A has no referent. We can get FA or not F of A. And so again, we have false laws of logic as a result of idealizations in the theory. So what I'm thinking here is, you might think that if A fails to refer, then F of A doesn't express a proposition, and so it doesn't get a truth value. Not F of A, and so that disjunction is going to come out, failing to express a proposition rather than as true. Okay, example 3. This one's a little bit more complicated. The idea that predicates are complete, meaning that their extension and their anti-extension, the set of things that satisfy P and the set of things that satisfy not P, exhaust the domain. So a third idealization concerns the between the extensions of predicates and the extensions of their negations, their anti-extensions. So in FOL, these exhaust the domain. It's not clear that natural language predicates interact with negation like this, and for various reasons. So here's one thought you might have. Some philosophers think that vague predicates may be incomplete, i.e. that there might be objects which are neither in the extension nor in the anti-extension. So sometimes people say this about color expressions. So if you think about the predicate red, and now imagine that you have like a spectrum of colored cards laid out in front of you. The one in front of you is like bright, bright red as red can be. The one at the far end is clearly orange, it's not red, and they gradually fade from bright, bright red to orange. You might think, well, the one right in front of you, red applies to it, it's an extension of red. The one that's orange, red doesn't apply to it, it's not in the extension of red. But some of the stuff in the middle, well, it's neither red nor not red, right? It's the rules of the language don't tell us that that thing counts as red, but they also don't tell us that it counts as not red. Okay, so that's a view that some people have about vague expressions. And so in those circumstances, you might think that the predicate red, its extension is not complete. The extension and the anti-extension don't exhaust the domain. There's a different motivation for the same sort of view about extensions being incomplete. Maybe with category mistakes, you have something like this. I can't think of my 2 examples in the paper, and I can only think of the complicated one. Okay, so you want to know if something satisfies the following. It's earlier than M in the alphabet, right? And so A is clearly earlier than M in the alphabet. Z is clearly not earlier than M in the alphabet. But then you might ask about, say, the exclamation point or the interrobang, right? Are they earlier than M in the alphabet? And you might think, well, it's just not defined, that predicate on those kinds of thing. Maybe there's a better example than that. But okay, you might think with category mistakes that they're defined on some subset of the domain rather than the whole thing, and there's just no answer to the question of whether the interrobang comes earlier than M in the alphabet. And so, a sentence that says that it does is not true, but neither is its negation. Okay, here's a third motivation for incomplete predicates in theories of truth. So Kripke's outline of a theory of truth used incomplete predicates to simulate the meaning of is true. He writes, a sentence such as one, most, i.e. a majority of Nixon's assertions about Watergate are false, is always meaningful. But under various circumstances, it may not make a statement or express a proposition. I am not attempting to be philosophically completely precise here. To carry out these ideas, we need a semantical scheme to handle predicates that may be only partially defined. Given a non-empty domain D, a monadic predicate P of X is interpreted by a pair, S1 and S2, of disjoint subsets of D. S1 is the extension of P of X, and S2 is its anti-extension. Px is to be true of objects in S1, false of those in S2, undefined otherwise. Okay, so we see how to construct a hierarchy of languages, each with a truth predicate that extends that of the last until we reach fixed points, in which the languages can contain their own truth predicates. Yet, even at the fixed points, the truth predicate, though intuitively more complete than it was, is not completely complete. Ungrounded sentences, including the truth teller and the liar, are neither in the extension nor in the anti-extension of true. It's fairly natural to think of the completeness of a predicate as coming in degrees, much as the straightness of a line does, or the flatness of a surface. For example, truth predicates earlier in Kripkean hierarchies of languages are less complete than those that come later. FOL deals only with predicates at the limit on this scale, fully complete predicates in which the union of the extension and the anti-extension exhausts the domain. On the assumption that natural language exhibits the features canvassed above, the SOL predicates are idealizations. And the most obvious law arising from the assumption that the predicates are complete is the law of excluded middle, so FA or not FA. If F is an incomplete predicate, and A denotes an element neither in the extension nor in the anti-extension, the law of excluded middle is false, since neither FA nor not FA is true. So with this idealization, we get a false law of logic. Okay, last example. This is like the last thing to do in the paper. So truth functional connectives. In FOL, they receive their meaning from the recursive definition of truth in a model on an assignment, which is a less pictographic way of assigning them the truth functions depicted by the familiar truth tables. There's something that I need to be especially careful about here. So Grice's logic and conversation taught philosophers not to argue from the fact that natural language connectives and formal connectives have different patterns of use to the conclusion that they have different meanings, right? He thought that disjunction and the English or had the same semantic meanings, and the difference in the way we use them was explained by implicature. And so if Grice is right, that natural language expressions have the same meaning as the truth functional connectives, the truth functional connectives in FOL are not an idealization of the natural language expressions. I won't argue then that the connectives in FOL are idealizations of their natural language counterparts on the basis of usage. But that means that the key to arguing that the formal connectives are idealizations lies elsewhere. For example, with demonstrating a difference in truth conditions, i.e. that substituting one for the other in a sentence can change the sentence's truth value, or showing that the epistemic and semantic consequences we expect when two expressions have the same content don't obtain. In the previous section, we already saw some reasons to think that the FOL treatment of negation is simplified. If some predicates are incomplete, FA could fail to be true without not FA being true. But the FOL truth table for negation left no space for this. For any sentence phi, if phi is not true, then not phi is, and vice versa. What what we need is a third truth status. Let's call it I as a placeholder, and a row of the truth table that tells us what happens if phi has that status. There are various ways you can go, but Kripke used the strong Kleene tables, which give us this. And then the classical table is clearly a simplification of this. So what we get if we add the assumption every sentence is true or false to our theory, and thereby remove a set of models, the set relative to which some sentences are assigned I. And now once we've assigned I as a possible truth value, the FOL tables for the connective specify only partial functions. We need to say what truth status each yields when one or more of its arguments is I. The strong Kleene tables give us one possible set of answers. And in that case, all laws that had non-empty premise sets survive, all logical truths die. So maybe a fact about strong Kleene logic, which you may or may not know, there are no logical truths in strong Kleene logic, but you get to keep all the normal classical entailments where there's something on the left. So you lose the principle of non-contradiction, which is 8. You lose the equivalence of phi and not phi, which is 9. And you lose this kind of phi if and only if phi when it's just on the right-hand side of the turnstile. So there are some things that are laws of logic and FOL, but you might think are not true if you accept that the classical connectives are an idealization of the English connectives. Okay, so here's what we've done. Cartwright argued that the use of idealization in physics led to some of its laws being false. I've suggested that we think of first-order model theory as simulating the relation of logical consequence on natural language and exploiting idealization to do so. When we do, we can see that a parallel argument applies. I've given 4 examples of idealization and the resulting laws that lie, which are false. Superficially, this might come across as a criticism of logic, but it's not intended to be such. Idealization is a useful tool in science and can be in logic as well. But more than this, I think we're sometimes afraid to admit that strong, simple logics might be false because we don't want to lose the simplicity and the explanatory power. But once we've seen the role that idealization can play and can admit that not all the laws of some logic are true and still continue to use it, where idealization is appropriate to our goals, I think we can lose some of that fear, and we can admit that the laws of that logic are false and still continue to exploit its usefulness. Okay, that's it. Thank you.